our neighboring department and come over, and he's going to tell us about two amusing problems. One is a one-sided problem, but no, it's two-sided in the end.
We'll see. Great, thank you all for coming. I thought that a useful way to present to you some interesting problems in physics was to divide this talk into two. The first half I'm going to tell you about a problem involving topology, minimal surfaces, dynamics, and things of that sort. And the second half I'm going to tell you about the physics of hair, and actually the statistical physics of hair. And it is an amusing problem, I think. Most people laugh when I tell them about this. So I'm going to start by describing to you a problem which has its origins actually in some, how should I call it, playing around that Keith and his former student Renzo Rica were doing. Oh, sure. Trying to understand an interesting problem in minimal surface dynamics, basically. As they were trying to do some early experiments on this, Adriana Pesci and I in the department realized that this was a really interesting problem and that we perhaps could help understand what was going on. So to put this in perspective, I want to just remind you of something maybe elementary. If I had a wire loop in the form of a circle and I dipped it into a soap solution and I pulled it out, you'd certainly agree with me that the structure that you'd get is a disk, a double-sided soap film spanning this, and that's a nice minimal surface with zero mean curvature. Now, on the other hand, what happens if my wire loop that I stick in there is actually a double covering of the circle, but not touching itself, that I pull it out a little bit and I dip it in the soap solution? What do I get? Well, it turns out that it's been well known for probably the better part of a century, if not longer, that you get a Mobius strip soap film. And actually, you usually get a secondary disc that cuts across it, and you poke it with your finger, and then you get a Mobius strip. And it's also been known that if you deform the wire frame that holds that Mobius strip enough, untwist it so that it's heading back toward a circle, this Mobius strip will become unstable. And somehow, magically, this surface will jump back to a two-sided solution. And this is what Keith and Renzo had known was the fact, and we were left with all sorts of interesting questions about this problem. And it's turned out to open up a whole set of interesting mathematical problems, which I want to tell you about. I'm going to give you just an overview of what we've understood so far. There are a lot of deep mathematical questions that I don't think any of us is equipped really to answer, but we can at least try to point the way through a combination of experiment and theory. Okay, so the first thing to say is maybe what I'll call an absurdly short history of the subject. I want to remind you of the incredibly long history of the study of minimal surfaces and give you a little bit of an opinion about where things lie. So of course we can go back to Euler and Lagrange, Plateau, Young, Laplace, all of those great men who first formulated the idea of calculus of variations and applied it to these kinds of problems. The very first Fields Medal that was ever awarded was given to Jesse Douglas for the solution of Plateau's problem, which is to prove the existence of a minimal surface spanning a given contour in space. And ever since that time, there have been huge amounts of work on classifying minimal surfaces, studying them in higher dimensions, looking at their stability, etc. But actually, back in the 1940s, Courant was the one who highlighted this transition that I just told you about, that actually there is the possibility of a slow deformation of the frame bounding the film leading to some kind of transition. And it's been, I think, unfairly neglected as an avenue of investigation. And so what I like to say is that despite all this intervening work, the simple question, what is the dynamical process by which a soap film Mobius strip collapses to a disk, had remained unanswered. Now here is Courant with Anneli Lax next to him, showing in a beautiful paper in the early 1940s, showing demonstrations that relate to the early paper in the 1940s about the fun that you can have with minimal surfaces. And I'll show you a few pictures from his paper. So here he talks about this double covering of the circle that I told you about, looked at from the side and from the throat. You see a hole through it. It's quite obviously a Mobius strip. And here he shows what's happened after the transition, where it's actually a two-sided solution. And his drawing is very interesting. And I'm going to show you that the key to understanding it is the mistake he made, in a sense, in not quite drawing what goes on right here the right way. And that's nothing really of a criticism of Courant. One needs actually the right kind of photography, the right kind of imaging, and actually to find the dynamical process you need a very high-speed camera, which he didn't have. But nonetheless, he raised all sorts of interesting questions, like, for instance, there are various frames that you can construct for which there are multiple solutions to the minimal surface problem. This is the so-called headphone soap film, where you have these two parallel loops, much like the catenoid that you might be familiar with, but you can have actually two possible solutions that are sort of trivially related to each other, and then a third one, which is actually a section of a torus. So there are lots of interesting questions about just the static possibilities given a frame. So in the lab, we've got the benefit of wonderful technical people who can make all sorts of interesting devices, and Colin Hitch in our machine shop made this wonderful little device. As you see from the thumb, it's a small little adjustable pair of wire loops that we can use to study just the simple catenoid problem and to look at interesting variants on it. And I'm going to show this first just to remind you of what happens when you take two wire loops with a catenoid spanning them and you just pull them apart beyond the point of stability. And it'll serve as a case study of how things are different in the case of the Mobius strip. Okay, so this is a movie taken at 2,500 frames per second. And as you watch this, you'll see that, of course, it collapses in this beautiful way right onto itself. Okay, so there's a critical distance apart for the two wire loops beyond which this is unstable. In order to visualize this at this high speed, we've done some interesting tricks. So for instance, you need a lot of light to photograph at 2,500 frames a second. And so we've dumped a lot of fluorescein, a fluorescent dye, into the film. We've also added glycerol to make it more viscous. And we've blasted it with blue light, which excites this fluorescence so that we can get these very nice movies. So there are all sorts of interesting things here, which have actually been studied in great detail, including by John Lister from our department, who's made fundamental contributions to understanding this kind of axisymmetric instability of a surface moving under the action of surface tension. But the thing I want to emphasize here is that the boundaries play a very passive role. They are holding the frame, they are the frame that holds the film, but they play no role really in the local singularity that forms here. It's basically the film contacting itself. So the first question that we tried to answer in this study of the Mobius strip was, where is the singularity in this problem? So I start with a Mobius strip, and about a tenth of a second later, this is what I see. It's a two-sided solution, very much like what Courant drew. You can see there's some funny business here. I'll get back to that. But the question is, dynamically, how does the stroke collapse? Where is that singularity? That was the first question. And a larger question is, does the nature of the singularity depend on the topology of the film? I can make all sorts of minimal surfaces and ask about whether the singularities have any general structure. And we'd, of course, like to know something about the dynamical evolution of the film. What are the power laws associated with this collapsing length scale? And I would actually add, more generally, what are the right tools to describe these processes? And can we deduce some general rules about predicting where the instability will occur? So the first paper we wrote, which had a lot of what I'll describe today, is here. And then we wrote in honor of this workshop that's here. We were asked by Nonlinearity to write a little overview about the general class of problems involving geometry and topology and constraints. Okay, so just to make it clear that there's nothing about the high symmetry of the catenoid problem that is making it collapse on itself. Here's, with that same little toy, not quite as good a movie, but here's a little movie showing you if I tilt it and make this lose its precise axisymmetry, it regains it by the time we get to the singularity. So again, the instability happens with the film collapsing on itself. And it's not just some trivial breaking of the symmetry that is giving rise to what I'm about to show. So here's a low-speed movie in which this is normal video rate, in which we simply deform the frame, and poof, there you see the singularity. And it's reversible. I'm putting this in a loop, but you can repeatedly do this over and over until the film drains. But basically, you can already see that the singularity is being driven to the boundary. And that's the fundamentally different thing about this problem. Okay, so now I want to just define for you, so we're all on the same page, the plateau border, because this is going to turn out to play an important role in this problem. So the most general description of a plateau border is when you have films meeting each other or a frame, it's a transition zone separating the film from the attachment to the frame. So if I took a cross-section of the wire and the film, here's the wire, there's some thick region of transition to the very thin film that you see later on. And that's the plateau border, and that is what I'm going to talk about as a way of understanding what goes on here. Okay, so now let's look very carefully using a very high-speed camera, 5,600 frames per second, at the collapse of this neck of the soap film. So the whole process takes about 1/10 of a second from the time that you get to the point of instability till the time that it's over. But thanks to modern digital imaging, it's very easy to study. And as you see with a bunch of reflections here to kind of guide you, there's a very smooth, nice collapse, clearly going to the boundary. This wire is about 1 millimeter thick, and then poof, there we are. And you'll see that there's some funny structure left here that's kind of wiggling around with the oscillations that were created in the film. And I have to tell you that for the longest time, this was the most confusing thing. We didn't know if this was a bubble, some kind of transient structure, but that funny light caustic that you see here reflects a very interesting pattern of winding of the plateau border around the wire in a way that we simply did not anticipate, and turns out to be the key to understanding what's going on. So if we take a close-up image, very close-up, of this millimeter scale wire, this is what we see. It is a static structure formed after the collapse. And if I look at the plateau border, which I see as a bright lime green color because of the accumulation of dye in that region, I notice that it actually snakes around the wire and comes out on the other side. And this light caustic is a consequence of a kind of fold in the surface, which is stable, and in some sense, if you believe, as I think we all do, that this is a minimal surface, it's a zero mean curvature area, but it's got very high Gaussian curvature in this region.
It's a zero mean curvature, even though it's dynamic.
This is static, so this is what's left after the collapse.
Okay.
Yes. So for sure, I often, when I've talked to pure mathematicians about this problem, they are used to thinking that everything's a minimal surface if it's a soap film, but it's not. Of course, once it's moving, it's no longer a zero mean curvature surface, because zero mean curvature is the condition of equilibrium. So only by the time it's stopped moving and settled down here is it again a minimal surface. Okay, so what we realized here, which was a hidden property of this problem, is that this plateau border is actually reconnecting in much the same way that you think about reconnecting vortex lines. So if I carefully trace what the plateau border is doing around the wire here, and I represent in just a schematic the wire in gray and the plateau border in red, what you see is that before the transition, when there's still the throat through the Mobius strip, the sense of wrapping is this way, whereas after the transition, as you see here, it wraps the other way. So the sense in which it twists around the wire frame has changed, and there's a difference of basically 2 pi in the way that it cycles around. So this is kind of interesting, and it was confusing to us at first how this related to the topology of the surface itself. And then we started playing around a little bit with a little analytic calculation that one can do. And this is motivated by some studies that Renzo and collaborators have done previously just about the general properties of curves that interpolate between a double covering of the circle and a single covering. So I want you to imagine a curve in space whose coordinates are given essentially as a kind of Fourier series in an angle that winds around the circle, so x, y, z. And it's actually a 2-parameter family with theta running around from 0 to 2 pi, and also a parameter mu, which for the moment I'm going to consider just to take the value -1. And when I do that, I actually trace out a curve in space as a function of this parameter tau. When tau is very small, I get toward the double covering of the circle, and as I increase tau toward 1, I get back to the circle. So this is like what I do experimentally as I open up this loop. And there's just a normalization factor here. And so this is a good candidate series of wires to look at the surfaces that may span it. Okay. Now, of course, one can try to find, analytically or numerically, minimal surfaces that span such a structure, but it's also possible to construct a ruled surface. Ruled surfaces are made of straight line segments. They're not actually minimal surfaces because the real surfaces are curved, of course, in important ways. But they are nice approximations, especially in the region of low tau and high tau, to what the structures look like. So they're basically like pieces of paper. And the way that one constructs a ruled surface is basically to go back to this parameterization and let mu run from -1 to +1. And as it does that, it traces out the line from one piece of the frame to the other. So we can study this using that method and learn the following. I want you to imagine that if mu equals -1 represents where we are on the curve, we could make mu equals -0.9, and then we're just slightly off the curve, but on the surface. And so if I do that, I could identify that line as a kind of surrogate for the plateau border, because it's just slightly off the frame. And what you discover is that if you look in the region where tau is near 1 and I have something that is close to the disk, you see the obvious fact that if I had drawn the plateau border here, it would just be a concentric circle with the wire as an outer circle, and the two are obviously not topologically linked. I could just pull them apart. But the surprising thing, which we confirmed at a 1 in the morning email with Keith, who had experimented, in his words, with loo roll and safety pins, is that if you look at the Mobius strip regime of the problem, the plateau border is doubly linked with the wire frame. And actually, you know this in a hidden way, because you probably all, especially in this audience, you've all done the experiment where you take a piece of paper in the form of a Mobius strip and you cut it down the center, and then you cut it again. And what happens when you cut it again? You get two of them, two loops, and one is doubly linked around the other. And that's the same action as separating the plateau border from the wire. And so this transition has a hidden change in the linking number of the plateau border from 2 to 0. And the twist that we see around the wire after the fact must be there to balance the writhe of the space curve elsewhere so that the linking number is 0 after the fact. And this was a real revelation to us and suggested that there's something much deeper going on here. Now, you can also try to calculate the sort of driving force responsible for this instability. So here I show you the area of these surfaces in units of pi as a function of this parameter tau for two classes of candidate surfaces. These are true minimal surfaces on those wires that I showed you parameterized, found with Surface Evolver, which is this wonderful program developed by Ken Bracke many years ago, which is a mesh, triangulated mesh solver for minimal surface problems. And you can calculate the area, or the energy, if you will, of these surfaces as a function of tau. And you find that in the one-sided regime and in the two-sided regime, there's a slight crossover in the middle where there's a very tiny energy difference and a coexistence between these two surfaces, and it's that tiny energy difference that's driving the transition. Now, the ruled surfaces do a pretty good job for very small values of tau and a pretty good job for large values, but they're not so good in between. But their basic structure is very much like what we see, so we can use them to guide our thinking about various kinds of singularities. Okay, now, there's a well-developed theory for the last 20 years or so on the kinds of power law singularities that should occur when I have a collapsing interface or a pinching drop or something like that. And from the work of Keller and Mixus many years ago, we basically know that if all I had in the problem was surface tension and the inertia of the air, which means I care only about its density, then the balance of forces should be such that any length scale in the problem, say the throat diameter here, should vary as the pinch time minus the actual time to the 2/3 power. So I have to construct a length out of surface tension, time, and density, and that's the only way I can do it. And so actually what we find for a number of experiments is that the throat diameter as a function of time minus our best guess of the pinch time, notice down to about 10 to the minus 4 seconds, appears to have a power law consistent with that t to the 2/3, meaning that asymptotically there's a balance between surface tension and inertia. But there's a crossover that we persistently see, such that at much earlier times, we see a power law more like t to the 1/3. And a heuristic argument that we've come up with is actually to think about dissipation in the plateau border as this film slides around the wire frame. And that you can use to come up with an argument that if h is a characteristic thickness of the plateau border region and mu is the viscosity in there, the balance between viscosity and surface tension would give a t to the 1/3. Now, to test this more fully, right now we're involved in experiments with different wire sizes and different viscosities to see if this makes sense. But there is an interesting kind of crossover here that we still need to understand more fully. Now, one of the interesting questions in applied mathematics that has been around for a long time is what are the nature of these singularities and whether you appeal to the full hydrodynamics or you look at simpler kinds of motions. These are interesting questions. Like, for instance, when I use Surface Evolver, it's essentially a motion by mean curvature algorithm. It takes the energy and tries to lower it by just saying velocity of points on the surface is proportional to the mean curvature, and therefore it tries to go to 0. So you might ask whether that algorithm actually does drive the singularity to the wire. It's not obvious that it will. One reason why it might have to do that is that this linking number that I told you about is defined at the wire itself, because it has to do with the plateau border and the wire. And therefore, if you change it, it must be singular at the boundary. But that doesn't mean that the first singularity that you see is there. But if you evolve it past the point of instability, you start to see that it does contract this throat to the boundary, suggesting that motion by mean curvature does go in the right direction. And we've had a wonderful second-year undergraduate student, James McTavish, over the summer, and we set him the task of trying to do this more professionally. And so using some more sophisticated algorithms within Surface Evolver and some fancy animation here, you can see how the throat, viewed from the neck region and from the side, does indeed collapse to the boundary under motion by mean curvature. And I'd like to believe there's a theorem here. And maybe one of you can help prove this statement. If I start with a minimal surface spanning one of these wire frames, and I go beyond the point of instability, that motion by mean curvature will drive the singularity to the boundary. There are lots of theorems about motion by mean curvature taking arbitrary shapes and rounding them up as they shrink, all sorts of things like that. This ought to be provable. And so if you have
Sorry,
any...
what defines the dynamics here?
It's just motion by mean curvature. Okay, so when I'm moving the wire, when I'm deforming the wire for different values of tau, the system will relax for tau away from the transition zone to a stationary state. But there's a point in tau at which I find no stationary state and I just run away. It's like pushing something off the table. At some point, it's going to fall. And so we're looking at the fall, where perturbations in the system drive non-zero mean curvature, and so it evolves. Right. So it's just that. Now, actually, the world of these minimal surfaces has much more than just Mobius strips in it. And there's a beautiful article by Almgren many years ago in which he pointed out that there's another interesting structure to consider. And I've got a little wire loop here, just like the ones we use in the lab. So you take a circle, you pull a tab out of it, and then you stick it back through. And you end up with this structure. And just like the Mobius strip often comes with a secondary film, this often comes with a secondary film. And historically, most people have decided that if you poke this secondary film one particular way, you get an interesting surface and you can look at that. But we discovered, somewhat accidentally, and this is really due to Adriana Pesci, that if you poke this film the way nobody considered before, you actually get a section of a Klein bottle. And a Klein bottle is two Mobius strips sewn together along their edge. And if you take two Mobius strips that you could have in the lab and you just sew them partially together, you get something that's topologically equivalent to this. And so this is this crazy structure. Now this is really interesting. It's got two of those potential singularities that the Mobius strip has, because it's basically two sewn side by side. Here's what the minimal surface looks like if you try to construct a tab coming off of a circle, poking back through and connect it together the right way. This is what's coming from Surface Evolver. So it's this very strange structure with this folding of the film on two sides around the Mobius, around the wire. And again, if you do motion by mean curvature, you'll find, and this takes a long time because this is a complicated calculation. Here you can see the triangulation. You'll find that actually the system exhibits two singularities. Mirror image on either side of the center mirror plane in the middle. And so it's not quite sufficient to say, well, the system has a certain linking number and it has to change and it has to go to the boundary, because here we have two singularities that occur. So actually this is a good illustration of what's going on. Using thicker wire, if we look down the body of this, you can actually see the plateau borders snaking around and doing their twisting around either side.
And film thickness doesn't change. You have finite thickness of the film,
Mm-hmm.
which changes.
Yeah, so the wire is much thicker, but the film is still probably tens of microns thick. And so if you watch this movie, which I think is playing, is it playing? Yes. So here you can see the wrapping of the plateau border on one of these wires. There's another one behind doing the same thing. So here's the wrapping of the plateau border before the transition. And it's kind of like pulling a glove through this structure. And by the time all is done, it actually wraps the other way. And then on the other side of that wire was that same singularity I showed you before.
Do they have to happen simultaneously, or can you break the symmetry so they don't?
They often happen nearly simultaneously,
They
but
don't have to. No.
they don't have to happen absolutely simultaneously. Now, actually, you can get some amazingly complicated structures out of this. So if you don't poke the secondary film that you get when you make one of these fine bottles, you get something that looks like this, which it's kind of crystalline looking. So there's a whole zoology of these different minimal surfaces that can be studied. And I think what we're trying to figure out is, are there general rules that will allow us to predict what's going on? And I just want to close by pointing out that actually there's some interesting fluid mechanics going on here as well. We recently decided to try to look at the collapse of a catenoid with a secondary film. So that's often what you find when you make a catenoid. And most people poke the secondary film because then you get a beautiful catenoid. But suppose you leave the secondary film in there. Well, now you have an interesting situation because there is also an instability, a critical distance beyond which this will go unstable. But now, as the sort of hoop tension on that outer part of the secondary film is contracting, the fluid has to go somewhere. And lo and behold, you get this beautiful fingering instability that is very much like what one knows from geophysical contexts, where you have a viscous fluid flowing down a plane and you get fingering instabilities. But here it's sitting inside this moving soap film. And I think this provides us with inspiration to study the fluid mechanics of these soap films much more in depth, because this was totally unanticipated. You can see it's gravity-driven since it doesn't happen on the top, it only happens on the bottom. So we call it the weeping instability. Okay, so that's sort of the first half of my talk, and it worked pretty well. I again tell you that these are unanswered questions in this field, despite decades, nearly a century of serious work on the minimal surface problem. These elementary problems, questions about how one transitions from one to the other, are basically unanswered. These experiments and a little bit of theory I told you give us some insights, but I hope we'll make much more progress in the future in understanding these general questions. Okay, I'm going to go on to part 2, if anybody has any questions. Yeah?
Have you maybe tried to put inside these soap films a frame in a form of a knot, like trefoil knot or something like that?
Absolutely. There are lots of things like that that could be done. We've looked at two linked loops, and actually it's extremely interesting. The way it transitions involves a kind of zipping transition along a linear plateau border. So it's extremely rich, and I think that's a good suggestion. Okay, so now I'm going to change gears and talk about a problem involving hair. And this involves not so much topological problems, but geometrical problems and statistical physics. And this is work that I've done with Patrick Warren, who's a scientist at Unilever near Liverpool, and Robin Ball, who's the head of physics at Warwick. And this grew out of Unilever approaching me some years ago to try to understand basic aspects of collections of hair. Now, Unilever is a company that makes soap and shampoo and personal care products, and they're very interested in what controls, for instance, the tangling of hair, and what do conditioners do, and how to make better products. And so they have a research lab where they have physical scientists, physicists, Patrick studied in the Cavendish, to try to figure this out. And they approached me to think about this problem, and we eventually turned it into the question, could we understand the shape of a ponytail? I forgot to bring my ponytail, not mine, but my sample. You've all seen ponytails. There might be some in the room. And when you think about it, the physics involved in a collection of hair is an interesting combination of the elasticity of the hair, gravity pulling it down, but more importantly, the fact that hair is wavy or curly. And this randomness, this random curvatures that are built into hair are what give it its body or volume. And so my talk is going to start with a little bit of motivation about why one would be interested in this, some facts about this, including the definition of a new dimensionless quantity in physics called the Rapunzel number, and a discussion of how this is a problem in what in statistical physics would be called quenched random curvatures. I'll show you that much of what we figured out, Leonardo da Vinci really knew, and ultimately we will formulate a density functional theory for collections of hair, out of which will come what is called the ponytail shape equation, which is a beautiful fourth order ordinary differential equation for the shape of the boundary of a ponytail. And from imaging of these real ponytails, we will determine what could be called the equation of state of hair, that is, pressure-volume relationships that are important in understanding what's going on. Okay, now you might ask, how on earth did this happen? And I got this email from scientist at Unilever. He basically said, I work in port sunlight, my background's in soft matter physics. Some of the challenging problems in the hair care area depend on us understanding hair array statistical mechanics. Under various conditions, from your publications, I see you have all these interests. Maybe you'd like to work on hair array statistical mechanics. And I really thought this was a scam, because I didn't know there was a field called hair array statistical mechanics, but there is, actually, and it's really deep. So you can, of course, look at popular culture and realize that in the animated film industry, the representation of hair, especially this kind of hair, is a challenging problem. And in fact, there's a very interesting group in Paris under Basile Auderly who have done lots of interesting studies of models for hair that can be used in computer animation. And here's a good illustration of what they're trying to achieve. On the left is a real model shaking her head, and you see the beautiful motion of the hair. And the question is, can one construct a graphical representation of all of those hairs that appears real? And it has to have the inertia of the hair, it has to have the interaction with the air, it has to have the tendency to clump together. It's a very challenging problem in computer animation, not to mention in physics, but they've already done a very good job, as you can see. So some of the motivation would be to think about these computer graphics problems, but also just to think about it as an interesting problem in physics. So I tried to find out who was it who first took good microscopic images of hair. And my friend, Professor Brian Ford, who's a great microscopist, said, Hooke. And so thanks to the Wellcome Library that owns all of this, it seems, one can look at the images in the Micrographia from 1665 in which Hooke says, I basically took some hairs from myself, some hairs that I had shaved off my beard, and I discovered that they were basically cylindrical, and they appeared not to be hollow. Some plants have, of course, hollow stems, but it wasn't like that. Actually, he discovered split ends. He said the top, when split, appeared like the end of a stick beaten till it be all flittered. Those are what we call split ends. So he really discovered a lot about hair, at least in terms of its microscopic appearance. But hair itself is extremely complicated. At the microscopic level, it's got a kind of hierarchical structure. Typical hair is about 100 microns across, so that's 1/10 of a millimeter. The structure involves these cortical cells, which have inside of them fibrils, and inside of them, ultimately, there are individual protein molecules of keratin that give it the elasticity. But when you slice hair and look at it under the electron microscope, it appears pretty homogeneous. And from our perspective, especially on the scales of millimeters and centimeters that we'll talk about it, it's just a homogeneous elastic material. But depending on where you are in the world, ethnicities and different racial groups, hair may be circular in cross-section, elliptic in cross-section, and this gives rise also to the kind of curliness differences that you see around the world. Okay, so here are some interesting facts. Those of us blessed with a full head of hair, like Keith, have something on the order of 50 to 100,000 head hairs. Now, hair, if you just took a few centimeters a month, it grows about 5 to 10 nanometers per second. Right? So that's like one protein molecule or two per second being added to your hair. So hair has a density of about 1.3 grams per cubic centimeter. The worldwide average major axis diameter is about 80 microns. And it has this wonderful linear mass density, 65 micrograms per centimeter, which is kind of useless to think about. But I like these units, grams per kilometer. Okay, so actually we all have, most of us in here have many kilometers worth of hair on our head, which is why our hair weighs many tens of grams. The bulk modulus is about that of nylon. And so you can infer from that the bending modulus, the coefficient of resistance to bending, that's about 10 to the minus 8 Newton meters squared. So the first thing we want to do is try to come up with a basic understanding of the length scales in the problem that come from balancing the resistance of bending and the weight per unit length. So imagine I had a filament lying nearly flat, and its displacement from a straight line was h of x. I looked at the energy per unit, the energy density along that filament. Well, the first piece would go like curvature squared, that's the resistance to bending, and the coefficient is that bending modulus A. And the second piece would be just the gravitational potential energy to lift it up in the field of acceleration g. And so if you just do dimensional analysis balancing these two terms, you'll see immediately that there's a length scale, a over lambda g, to the 1/3. And that length scale, script L, for these numbers is about 5 centimeters. And that's the length scale below which gravity will not deflect the filament. So if I took any one of your hairs and it was less than 5 centimeters or so and I held it out, it wouldn't matter in what orientation I held it, it would basically go straight out from my fingers. If it's much longer, then it will be deflected by gravity. So it's natural, especially since in fluid mechanics, most interesting numbers begin with an R and then an A, to define the Rapunzel number as the dimensionless length of the film, of the bundle. So it's the length of the bundle divided by this characteristic length. So people with a crew cut have a Rapunzel number of maybe 0.3 or something, and Kirsty back there, covering herself, has a Rapunzel number of probably about 6 or 8. Okay, so the second thing to say is that this is a problem in statistical physics, and this is where I didn't understand at first how rich the problem was. But if you grab the hairs from anyone's head or from standardized switches that you can buy from suppliers, and you look at the individual fibers, I've thickened them here just to make it easy to see, they have a whole range of different built-in curvatures. Now these are sensitive to humidity and method of preparation and your emotional state probably, but they are generally quenched, that is, they are fixed in the system and not in thermal equilibrium in any sense, because these are macroscopic objects. So when I want to put together a whole bunch of these hairs, they are going to push against each other and resist being confined in the same region because they may be intrinsically bent, but they also resist any further bending. And so I have to do work to compress it. And that pressure pushing out against any attempt to compress is what will swell the bundle from its otherwise simple shape. So just to put this in perspective, here's a somewhat busy slide, but meant to show you in a nutshell the difference between how you have to treat a system with quenched random curvature and annealed random curvature. So imagine, again, here's my elastic filament, but suppose it was a system in thermal equilibrium. So here's my height function, h of x. The projected length deficit, the difference between the actual arc length of this and the projected length, is a measure of the extra length I've created. And if I had a force pushing on this filament, then my two contributions to the energy would be the resistance to bending and the work done by that force in compressing the filament. And so I could ask if I just resolve this into Fourier modes, not worrying too much about boundary conditions, I could use equipartition in statistical physics.
Small deviation.
For small deviations, yes.
All this is for dry hair.
Well, right now this is for a fictitious microscopic hair in thermal equilibrium, but absolutely dry, yes. Somehow it's in a heat bath, okay, so it's the air that's providing it. So what I would do is I'd say, well, the Fourier modes by equipartition have to have 1/2 kT's worth of energy, so I can write down the expected mean square value of the Fourier coefficients, and it looks like this, kT divided by that same factor. And so if I integrate up, I'll discover that the projected length deficit at large forces goes like 1 over the square root of the force. So I will have to put an ever increasing force to actually straighten this thing out, and that's the rule. And this is known as the worm-like chain in polymer physics. But that's not what I have here. I don't have an equipartition rule to apply. What I have is something like this. I have an energy which is actually the curvature minus a local value of the preferred curvature. So this kappa 0 may depend on where I am, giving rise to the preferred curvature. That thing squared, and then a force pushing on it. And now what I do is I say, well, the Euler-Lagrange equation for this will give me this fourth order relation. Now I can solve that formally for the square of the Fourier amplitude, and it looks sort of qualitatively like that, but now it involves the spectrum of preferred curvatures that is handed to me from the start. And so then I can do the same calculation. I discover that at high force I get a very different force law, where what I care about is the spectrum of the intrinsic curvatures in the problem. So the force laws are extremely different by virtue of these two different constraints. And in fact, we're trying to test this right now by pulling on real hair. Okay, so if I take about 120 hairs from one of the commercial switches that we use to study hair, and I take images of them, and then I overlap all those images, each one in isolation, I actually get something that looks a lot like a ponytail on the side here. And that's because this issue about quenched versus annealed curvatures is a little more subtle than I said, because you all know, you comb your hair in the morning after washing it, and it stays where you put it. And it does so because there's a glass transition that happens in hair as a function of humidity. So once the humidity goes below a certain point, those curvatures are locked in place. And so when I clamped the ponytail after washing it, I ended up locking in place a gradient of intrinsic curvatures from the top to the bottom. And so in principle, this is a slightly history-dependent problem, but we're not going to delve too much into that at this point. Okay, so here, for instance, is a little movie showing 115 hairs that we've taken from a commercial switch supplied from Glendale, New York, in which you can see, hanging from the top, how there is this spectrum of curvatures, nothing too terribly curved here. And we can look at, statistically, say, the mean square deviation of this filament from the straight line hanging down as a function of arc length along the filament. And you see that it progressively increases. Of course, we lined up the filament so the bottom was called 0, so it eventually dies down. But this steady increase is what I was describing before. And you can turn that also into a measure of the curvature spectrum. And you see the typical values are about 0.1 and 0.2 inverse centimeters. Now, what I should say is that it's not a trivial thing to actually do this imaging. We have a stereoscopic imaging system that reconstructs the three-dimensional shape from two orthogonal directions and does so in a manner that's very reliable. So the spectrum of lengths that we get out of this is very tightly clustered around what we know to be the mean length in the system. Is there a question? No? Okay. Okay, so here's how you might formulate the very simplest density functional theory for the shape of a hair bundle. And the bottom line, of course, is that we do not want to deal with, say, the 10,000 separate hairs that make up this beautiful ponytail. We want to have some kind of averaged theory. So we've concluded that one way to begin is to assign two quantities to the hair bundle locally. One is the average direction in which the tangent to the curve of each filament points. We'll call that T. It's the local mean orientation of the fibers, and it depends where I am in the filament, in the bundle. And the second is a fiber length density, which you can think of as the number per unit area crossing a plane perpendicular to the fibers. It ought to be possible to construct a theory based on these two quantities. And it starts to smell a little bit like fluid mechanics, in the sense that this is like a velocity field and that's like a density. And in fact, the absence of free ends implies a divergence-free condition on the product of the two, which is kind of interesting. So the hypothesis that we have,
And T and minus T not equivalent? T and minus T not equivalent?
no, because I've got gravity breaking the symmetry. So what I'd like to do is imagine, this is where we're going to start, that there's some kind of local energy functional I can associate with this bundle, depending upon rho and T. So basically, I'll integrate over all the bundle. I'll count how many fibers there are, and then I'll associate an energy which first of all involves the bending associated with the mean orientation of the fibers. So there's a bending constant and the curvature squared related to the gradients of the tangent vector. There may be a gravitational potential energy acting, fine, or electric field. We could put our hands on a Van de Graaff generator and put charges on and see what happens. And then we're going to throw all of our ignorance about the disorder in the system into some local energy functional U. And we're going to see where that can get us. So the idea here is to partition the filament orientations into a mean, described by T, and the deviations from it that are somehow capturable in a local energy functional. And if you do the calculus of variations on this, you'll discover that if this U is viewed as a function of the density rho, then the pressure in the system is this derivative of U. And this is a standard result in the theory of fluids. Okay, now it's really a complicated calculus of variations problem, but I do want to point out that Leonardo seemed to have the same idea. So if you look in his notebooks on the proportions and on the movements of the human figure, and if you call up the Royal Collection, they'll give you permission to reproduce this beautiful image from his notebook, a very famous image. It is believed that this is a self-portrait of Da Vinci, and it's also believed that he's not actually looking at what's on the right-hand side here, but we can believe that he is anyway. What he describes here is the motion of water past the supports on a bridge. And he says, observe the motion of the surface of the water, which resembles that of hair, and has two motions, of which one goes on with the flow of the surface and the other forms the lines of the eddies. So there's kind of a mean flow, and then there's all the stuff around it. And that partition is what we're going to use here. Okay. Now I should say, our original idea was to postulate an energy functional U, derive from it a force balance equation, and then compare it to experiments. But I'm going to show you that that's not the way to go, and we're going to turn the problem around. But to make some progress, we have to make some approximations somewhere, because this problem is too wide open otherwise. So the first thing is just to introduce the quantity n, which is the number of fibers within a radius r at depth z. And if you just do a little counting, you'll discover that rho and the local direction theta are related to derivatives of n with respect to r and z. And in that sense, n looks a lot like the stream function in fluid mechanics. And so the simplest possible approximation you could make is that the number density of filaments is constant. That's surely not the case right near the edge. But let's just try that approximation. So in other words, the number inside a circle of radius r is just r squared. It has to be scaled by the actual radius at that point, and then multiplied, of course, by the total number of hairs in the bundle. And that ansatz of self-similarity is also equivalent to the statement that the tangent angle just interpolates linearly from whatever it is at the boundary, dr dz, of the bundle back to 0 as just r over the radius. So it just moves out monotonically and smoothly. So if we substitute this into the governing equations, then having done all the integrations over space, we're left with a single integral down the filament, and all that appears are the function r and its derivatives. And this is what that effective energy looks like. It's got an n in front, a d arc length coming down, and then what looks like an equivalent single filament energy, in the sense that here's the curvature squared of the edge with an effective bending energy that's just a factor of 2 different than the original one. Here's the tension in the filament multiplying the metric factor. The tension in a filament starts out high at the top, goes to 0 at the bottom, just by local force balance. And all that's happened is that the mass density has been renormalized by a factor of 2. And then here's our local energy functional. So having made this ansatz of self-similarity, the problem is reduced to the shape of the boundary as an equivalent single filament problem. We still don't know what this is, but if I now vary this functionally, the Euler-Lagrange equation can be written this way. The second derivative gives me 4 derivatives on the shape, multiplied, I've rescaled it here, so I'm multiplying by my 5 centimeter length L cubed. There's a piece involving the second derivative and the first derivative that come from the variation of this. One you can think of as the tension, one you can think of as the weight. And then all that shows up here is the derivative of this guy in the form of a radial pressure pushing out. Now, I don't know what it is. It's some function of r. If I told you u, I'd tell you pi. And it's here that actually I can make some comments about the historical connection. So up to here, this is a very well-studied problem. There's a problem in Landau-Lifshitz you can look up, which is the buckling of a column under its own weight. And if you just reverse the signs of things, you get that equation. And actually, more recently, it's been studied in the beautiful book by Oderly and Pamo for curly hair and other interesting variations. But fundamentally, this is a well-studied problem. And the idea that there is a pressure in the system and that there is an equation of state goes back to Van Wyck in the late 40s, who thought about this in the context of wool. You'd like to know how compressible wool is to understand its insulating properties. And there's some very interesting work by Beckrich et al. Recently who looked at a 2D problem of hairs where they bump into each other just because of nearest neighbor interactions, and the idea of a pressure also came up there. So as I say, our thought was, look, we'll make a model for this pressure, we'll try to compare to experiment, see if we can test it. The problem is that it's very difficult to take an image of a ponytail and from it extract with reliability the fourth derivative of that shape numerically from an image. It's just really hard. So it's very hard to figure out all the terms going on here and try to make some sense of what's important. But if you look at representative values of this pressure, and I'll come back in a moment to what they are, you discover that those 4 various terms vary in importance with respect to arc length from the top of the ponytail, where it's clamped, to the bottom in an interesting way. And here you see them. And the first thing to notice is that near the top, we have the pressure pushing out, and we have the elasticity resisting it. And gravity, the weight, is subdominant. And that's because near the top, we're on a length scale smaller than that little script L, so effectively the Rapunzel number is small. So actually, at the top, it's a balance between elasticity and pressure. And that's what gives rise to the very simple straight geometry you see. But once you get past that length scale, most of the rest of the ponytail has a balance between pressure and weight. And elasticity is subdominant. So somewhere in this problem, there's actually a matched asymptotic analysis to do between the two ends. So what that means is that if I wanted to understand the actual pressure in a ponytail far away from the clamp, I could ignore this term. And if I knew the shape with enough reliability to measure the second and first derivatives, I can read off the pressure. And so that's what we did. So you take lots of ponytails, and you image them. You rotate them 5 times around to get a rotational average. And then you graph the radius as a function of coordinate down the length, z. Here you see 4 or 5 ponytails and a simple polynomial approximation to that. And from this, we just read off the pressure as a function of r. Now, if there had been no swelling pressure at all, if I had solved the problem, the Landau-Lifshitz type problem, my ponytails would have been hanging much straighter, in fact, this much straighter. So all of this outward pushing is a consequence of the self-avoidance and the intrinsic curvature of the filaments. And in fact, the equation of state that Van Wyck cooked up for wool long ago doesn't really match well either. So let's do this. We'll read off pi of r from this function of the shape. And what you discover is remarkable. You discover that pi, as a function of the radius, is a straight line. That is to say, it looks like some prefactor 1 minus r divided by a characteristic length scale r star. Now this, my friends, is called Hooke's law. Right? So we've gone full circle back to Hooke. And we should have known this in the first place, but that's the way research often is. So basically, if you compress this bundle a little bit, it's going to respond like a spring. And so what's interesting is what is the prefactor, and can we interpret it? And along the way, then, we can do what Patrick Warren calls the experimentum crucis. That is the crucial test of whether this is anywhere near sensible. You take real ponytails, whose Rapunzel number is around 5, and you slice them back progressively. And you look at the sequence of shapes that you get, and then you do the same in the theory. So you start with a set of parameters, pi 0, r star, and you look at the sequence of shapes that you get as you chop it back. And as you see, if you assume a constant pi 0, you're fairly close to what we see experimentally. And if you grade the prefactor of that, because the intrinsic curvature varies with position, you do a bit better and get something that's a fair representation of a real ponytail. And you can see at the top that it basically flares linearly. Okay, so this provides us with a sense that this is a reasonable approach to ponytails. And then the final question is, well, how do we interpret that prefactor? And I think the answer is very simple. We imagine that what's going on here is that the intrinsic curvatures are being squeezed by neighbors that are impinging on the hair. And so we start with the simple problem of a curved filament, which has a preferred curvature kappa naught, that is confined between 2 plates, a distance d apart. So for instance, in order to have that shape, it would be a parabola. And if we know this energy, we can then calculate this general energy. Then we can calculate what the energy looks like when so confined. And it looks like 1 minus d over d star squared, where d star is related to the intrinsic curvature. And that is exactly the form of energy you'd get also if you took a helical filament and confined it in a cylinder of radius a naught. There's an energy that looks like 1 minus a over a naught squared. And in both cases, the prefactor is basically the elastic constant and the mean of kappa naught squared, the mean square curvature built into the system. So we can also look at experiments, and from this and from a sum rule that relates the pressure that we have to the internal energy in the system, we can actually find the equivalent size of the confining cylinder in our ponytail problem. And it turns out to be something like 40% of the radius of the actual ponytail. So the picture we have here is like a problem in polymer physics. Rather than nearest neighbors bumping into each other and confining the filament, it's some further out collection of filaments that have confined them, but it's definitely smaller than the radius of the ponytail. And it's this confining effect of collisions with the neighbors that's giving rise to the swelling pressure and gives rise to this basic feature of the ponytails. So there's a huge amount to do here, both further investigations of this energy functional, but also things like the dynamics of hair. In fact, Joe Keller from Stanford, the very distinguished applied mathematician I'm sure you all know of, has done some very nice work a couple of years ago on the swing of the ponytail. So person with a ponytail goes jogging down the street, their head is moving up and down, and of course the ponytail goes side to side. This is a beautiful problem in parametric excitation. It's also got a progression of models from something you read in Landau-Lifshitz to something more complicated. And it suggests that actually there's a new field of physics, which is soon to be highly popular, I'm sure, which is called aerodynamics. Great, I'll stop there. Thanks.
Well, wonderful. Yes.
Well, it looks like you always cut at some finite z, but if you went to infinity, it would become just a cylinder or something like that. No?
That's exactly right. In fact, that's what Rapunzel has. I mean, if your hair is 5 meters long, yeah. And the answer is that there is a radius at which the pressure goes to 0.
Yeah. Okay.
And so then you just hang straight.
And about hysteresis, when we comb the hair, apparently we cannot come back to the former.
Okay, so this
To describe it.
Well, okay. So the original problem we proposed at Unilever was to understand tangling, and we thought that actually we took hair samples and combed them in front of our eyes carefully. And what you understand is that you end up creating sharp angles between the filaments by virtue of diverting them around the teeth of the comb. And a tangle or a knot is not a real topological knot. It's a frictional lockup most of the time. And it's called the capstan problem in sailing, where you have a rope around a pivot point and you get a lockup. And so basically I think what's necessary is to understand the sort of frequency and distribution of collisional angles inside one of these things to understand the circumstances under which you get that lockup. And that's what we're trying to do now, actually.
Real ponytails are not don't just hang down; they lift up. And
Absolutely.
now that's probably a simple extension of your theory with the initial conditions given the equation of state. But do you get that shape?
We've looked at that a little bit.
It hangs.
Yeah, we've looked at that a little bit, and you'd like to believe that you could construct a kind of similarity solution that rides along with that.
Yeah.
And I think you can. And we haven't studied it a great deal, but we certainly thought about it. So you're absolutely right. They usually come off the side, right? Or this way.
Unless on the pony.
Yes, right.
And twist and elasticity not relevant here?
Yeah, so actually when you think about constructing the vector, the energy functional out of this combination of rho and t, you could imagine putting torsional contribution, and certainly many ponytails, including the one back there, often have a certain amount of twist to them. So that would be interesting too. Yeah.
I have a question about the first part of the talk. Sorry, I have to take you back there. You showed a crossover point, which did I understand right that it was where dissipation takes over rather than?
Well, that's what we think is going on, but I'm perfectly willing to be proven wrong there. What we found is that the time evolution of the collapsing neck has a time scale of about 0.01 seconds, where it seems to cross over from one power law to the other. It's also a point where the Reynolds number is suddenly about 1 of the collapsing dynamics, at least as viewed in terms of the neck size and the velocity. So it could be something else. I mean, it can be stretching in the film or some kind of complicated dynamics associated with fluid motion in the film.
Yeah, thank you.
Yep.
Yes.
If I'm allowed to jump back to hair.
You have soapy hair? That's good.
So this prefactor, I guess, is basically Hooke's constant or somehow related to Hooke constant, right? Must depend on the property of
Absolutely.
the hair. In particular, let's say horsehair has different elastic properties, as we know. Where exactly? I guess I didn't see exactly.
Okay, so there are two things that matter in this interpretation. One is the bending modulus. So the bending modulus is the Young's modulus times the 4th power of the radius if it were circular. So there's a very strong dependence on the radius. So perhaps horsehair is bigger in cross section. I'm not sure. Could be. And the second thing is basically what is the average squared curvature. So this is what you could use as a simple way of characterizing, say, Oriental hair versus Brazilian hair. There's a huge difference in the mean square curvature, and that gives rise to a very different pressure. Obviously, there's more to it than that, but that's at the most basic level. That's the sort of intuitive picture of what's going on.
Well, wonderful. I think we're all stunned.
Well, I hope you're amused. That's my hope.
Certainly amused. And actually, I think you said geometrical, but there are topological aspects in this as well,
For sure.
really.
Yeah.
I mean, braiding.
Yes.
And the funny thing is, there's been a lot in this program about open knots.
Mm.
You know, knots that are local and with ends that are not closed, and how to characterize this. And this problem is arises very naturally here as well. So really, it does fit very well in the program, as of course the first subfill part. So thank you very much. Wonderful.
Thank you.